need to define a couple things about the minimal polynomial for you guys. What is the minimal polynomial, for example? This would be a good question to answer. So before that, so basically we're in section 6.5. I just have a few remaining tidbits to go over. So first of all, definition. If we have a linear transformation T from B to B, all right, then we talk about the ideal. The ideal of T is, well, the notation in this book at least is IP, I of T, and that's equal to, it's the set of polynomials, basically Q, Q of T and the polynomials over F. Well, let's see here, he uses this notation, polynomials over F, such that what? So how do you, what does it take to be ideal here? Being the ideal, you simply have to do what? You have to do what? Q of T equal to 0. So, for example, if T had a matrix which was, for example, 2, 0, 0, 3, fine if you want, I can say the matrix of T is that. Then, for example, you could see that if you had Q of T equal to what? Like, how about T minus 2 times T minus 3 squared? That would, for example, be in this ideal. Because what we mean by Q of T is this. So if you look at that specifically for this matrix, what's T minus 2i? We view this as, I mean, slight abuse of notation here. I'm identifying the matrix with this transformation for the sake of brevity. But, well, fine. I'm feeling guilty. The matrix of Q of T would be what? It'd be the matrix of this times the matrix of that. What's the matrix of T minus 2i?
0, 0.
Yeah, 0, 0, 0, 3. What's the matrix of T minus 3i? Well, it's...
It'd be a 1.
Yeah, it'd be a 1. Instead of 3.
Oh, sorry. Not you guys. See here. 2, 0, 0, 0 squared, right? And you can easily calculate.
Wait, not did. Never mind.
It'd be -1.
Yeah,
Oh.
yeah.
Stick to your guns then. So anyway, you multiply these out, you get 0, right? Now, I guess this would be more exciting if you multiplied this out, right? I mean, Q of T is what? T minus 2 times T squared minus 6T plus 9. So that's T cubed minus 6T squared plus, almost certainly, foolish use of that kind of element, minus 2T squared plus 12T, even more foolish to comment on it, minus 18. So that polynomial, for example, is an ideal generated by T. All right?
When did number theory and linear algebra coincide?
Let's read the book.
Wait, number theory and linear algebra coincide?
Proposition.
I meant the one.
Worlds collide. Proposition A, this ideal generated by T, is a vector subspace of the polynomials over F. Right. And B, if P of T is in the ideal generated by T, and Q of T is anything, any polynomial. I'm not super keen on this notation for polynomials. Like, I really like the notation for my ring of polynomials to include the indeterminate. The indeterminate here is T, but there's no notation to indicate that little t is the indeterminate. It's kind of, anyway, we're just on this for a day, so I won't quibble. I'm just going to tell you there's better notation as we go on. Because P of F is a temporary and impermanent notation, okay? Anyway, then what? If you've been a number theory, you should anticipate what? P of T times Q of T squared.
Denominator of IT.
Right. So, and we have another proposition. That's really easy to prove because basically, if you have a sum of things which are 0, they're still 0. And if you multiply any polynomial by another polynomial which goes to 0, the fact that P of big T is 0 forces P of T times Q of T to be 0. It's this polynomial multiplication commutes. Proposition is really easy to prove. Proof's on page 288. Proposition 6.5.4, though, I'm going to jump ahead, is the division algorithm. So if P of T and S of T are any two polynomials over F, then there exists unique polynomials Q of T and R of T, such that what? S of T is equal to Q of T times P of T plus R of T, where either R of T is equal to 0, or the degree of R of T is what? Yeah, less than the degree of T. For example, in the book he works out that t to the fourth minus 3t cubed plus 2 divided by t squared plus 2t. Basically, the calculation of it shows that that's equal to t squared minus 5t plus 10. He does this by log division on page 288, and then it's not done yet. Plus parentheses minus 20t plus 2 divided by the dividing polynomial, which is t squared plus 2t here. So that's what we would have done, say, back in pre-calculus or something. This Q of T is called the quotient. R of T is called the remainder. So in this example, let's see here. Which one's Q? This is the remainder here. Right, so to discover this equation, what do you have to do? You have to clear out by the dividing polynomial, which here is what?
T squared plus 2.
Right, that's the P of T. Right? So we have t to the fourth minus 3t squared q cubed plus 2 is equal to t squared minus 5t plus 10 times t squared plus 2t plus parentheses minus 20t plus 2. And that's the division algorithm for polynomials. You do it just like you do for integers. Right? Essentially, log division is almost the same, except you have to group powers of t rather than powers of 10. Right? I mean, right or wrong, it's there, it's unique. Okay, so given that, which you may or may not be familiar with, and we'll do a lot more with this in Math 422 if you take it. that leads us to proposition 6.5.6, which simply provides the existence of a particular thing. Proposition 6.5.6 says, if you have an ideal, so let I be a subset of the polynomials over F, and let that be a subset for which what? Such that, first of all, I is a vector subspace of P of F, so it's closed under addition, and Uber closure, as Bruno called it. So P of T, an element of I, and Q of T, just any old polynomial, has P of T, Q of T, an element of I again, all right? Then what? Then there exists a unique polynomial, G of T, all right? Such that what? Number one, G of T divides F of T for all F of T in the ideal. And two, G of T is monic. What does it mean for a polynomial to be monic? Degree, not, well, no. Could be degree 32, so whatever.
It has one root, maybe?
Nope.
Not without.
Yes.
It means the coefficient of the highest power is 1.
Right, the leading coefficient has to be 1. So like, let's see here, for example, monic, monic, monic. Oop, not monic. Because the leading coefficient here is 20, minus 20. But these, this, and this are all monic for what it's worth. Bela, can you see the purple right now? All of it?
Yeah.
Okay. So basically, if you have an ideal, there's like this smallest polynomial in it, all right? And the smallest polynomial you can use through multiplication of other polynomials to generate everything else in the set. So if you're a number theory, what we're saying here is that in the ring of polynomials, every ideal is principal. And the generator of that principal ideal is what we call it's called the minimal polynomial. This G of T is called the minimal polynomial. Actually, that's a little bit more specific. Usually minimal polynomial is given with respect to a linear transformation. And so that brings us to really the definition we're most interested in here. But I have to say some of these things, otherwise you won't quite understand the definition I'm making now. Well, you may still not understand it. That's okay. I need to erase something here. I'm going to erase the example. Ooh. I would probably want that to still be there. Keep that there. So definition. This is definition 6.5.7 on page 289 of Damiano and Little. It says the minimal polynomial. The minimal polynomial of T, which is again a linear transformation on a finite dimensional vector space VZ. All right, is the unique polynomial G of T, an element of IT, such that what? One, G of T divides F of T for all F of T and IT. And of course, two, G of T is monic. All right, let's take a breath here and see if we can make sure we understand what we're saying. Did I guess that?
So the proposition 6.5.6 If we prove that, then we have this definition, or is this like how it looks like it's comes together?
Right. The proof of proposition 6.5.6 is it's there on page whatever it is. It's pretty straightforward. It's actually the same proof that you'll see in number theory to prove that an ideal of the integer is principal. Basically, you suppose that there is the smallest degree polynomial which generates the ideal, and then look at the division algorithm. And if there's a remainder which is non-zero, it implies the existence of a smaller degree polynomial which generates it, which is a contradiction. Therefore, it has to exist and do so uniquely.
Okay.
But the proof is pretty standard. But kind of beside the point here, it's not something I would test on, because it's really outside our skill set here, which is what makes it interesting that this is part of the course, in some sense. So the minimal polynomial T is this unique polynomial such that, now what is IT here? Remember the definition? IT is what? It's polynomials such that Q of T is equal to 0, right? So can you think of a particular polynomial which is in IT?
The characteristic polynomial?
Right, so observation, exactly, observation. And so how do we define the characteristic polynomial? We say P of T equals the determinant of T minus Pi, if you like, as P of T. Now, I think there's something deceiving here. When you, and I've tricked myself this too, like, I say this has P of T equals to 0, and you're like, well, of course, because if you put T here, then you get T minus T, which is 0, so it's 0. That's not the logic, though. You really have to filter through. This is some polynomial, right? So it's like, it's minus T to the n power, excuse me, depends on the dimension of B, right? Minus 1 to the dimension of B, T to the n, plus other coefficients, right? Like Cn minus 1, T to the n minus 1, plus da 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 da, plus C1T plus C naught. I mean, there's some polynomial which is, there's coefficients when you calculate that characteristic polynomial, as you guys are currently in the midst of in your homework, right? You felt the pain, calculating the characteristic polynomial, you know what this means. There are coefficients, they're not pleasant to find, but you can find them nonetheless. And so when I say P of T equals to 0, I'm saying a really different thing than just plugging T into this formula right above. I'm saying P of T, which is minus 1 to the dimension of B, T to the n, plus da da da, plus, C1 times T, plus C naught times the identity transformation, where T to the n is understood to be the composition of T with itself n-fold times, right? So and that's, of course, what? We proved this the other day, right? What is this leap going from this has is what's supplied by that? What's the name of this?
Cayley-Hamilton theorem.
Yeah, this is the exactly Cayley-Hamilton theorem, which is a non-trivial result. Right? We had to work to prove that, and I didn't even do all the work. All right. Anyway, the point is, characteristic polynomial is in there, right? Yeah.
So this is kind of one of the motivations for why we take the Hamilton theorem as important.
Yeah, I mean, it's central to doing anything with this kind of technology. It's true. So, all right. So let's get to the point. For a given linear transformation, how do you find the minimal polynomial, and what does it have to do with the Jordan form? All right. Let me just tell you. I'm not going to be able to prove everything today. I still want to help you guys with your homework, so let me just spill the beans, so to speak. Quote my uncle. So, first of all, the fact that the characteristic polynomial is in IT, that means, well, the minimal polynomial does what? The minimal polynomial divides everything in IT, right? So what that says is that there's a particular factor, right? If you have, for example, T minus lambda, if that's a factor in the characteristic polynomial, right? That implies that T minus lambda must also be a factor in the minimal polynomial. Because the minimal polynomial divides everything, and if it didn't do that, then minimal polynomial wouldn't be able to divide the characteristic polynomial if you think through it. But we know the characteristic polynomial is in this IT, so it has to have each factor. Just if you think about polynomial factoring, certainly the minimal polynomial must have each factor that's present in the characteristic polynomial. not counting multiplicity. All right, so they have to share the same zeros, but they don't have to share the same multiplicity. Over here in my initial example, this was on purpose. This Q of t is not the minimal polynomial. You can see here, I could erase the 2, right? I could take this 2 and I could go chop, 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 and I'd still get 0 here. So as you can see, in fact, g of t here, and this is at the honest to goodness truth, g of t here would be t of t minus 2 times t minus 3. That's the minimal polynomial for this guy. All right, so yeah.
So like with the minimal polynomial, give us have something to do with the cycles then?
Yes, let's get into it. So here's how it goes. So in short, g of t. So if t has distinct eigenvalues, lambda 1, lambda k, distinct. So suppose you have distinct eigenvalues, lambda 1 through, and I'm still assuming that we're in the easy case that all of our eigenvalues are in the field, all right? There's some modification of this that you can make in the case that you have complex eigenvalues, right? They gotta come in conjugate pairs if your mapping's real, so you can still say organized neat things. I'm not trying to say those things right now. G of t then, assuming that all the eigenvalues are in the field we're working in. So g of t will look like this. It will look like t minus lambda 1 to the k1 power. Well, I need some other notation here. Let's say, have I used k sub 1 as something else, maybe? We used it for nilpotent cycles, but that's not this context anymore, so I think it's still okay. I can use k1. T minus lambda 2. Is this k bothering you? I'll be something else, okay? I don't know. I need a letter.
Star.
I'll take an L1, thank you. L2, da-da-da, T minus lambda k. Lambda k to the L sub k. Where we have 1 is less than or equal to L sub j is less than or equal to M sub j, where this is the dimension, it's the dimension of the generalized eigenspace k sub j, which, by the way, is also equal to the multiplicity of t minus lambda j in p of t. So the most it could be would be like if your characteristic polynomial, for example, has t minus 3 cubed. The most you can have in your minimal polynomial is t minus 3 cubed. But you might have t minus 3 squared, or you might have t minus 3. But it's got to be somewhere between 1, because they have to. Minimal polynomial has to have all of the roots that the characteristic does, but then it can also have some of the multiplicity, possibly all, but not always all. So then how do you decide? Like, what defines this L? What actually is L sub I, L sub j? And so this is the thing that's proved in this section. It's not that hard to prove, but as I've mentioned, we're out of time. L sub j is simply equal to size of largest Jordan block for lambda sub j. Just that. So let me just illustrate with examples. That's the easiest thing to do. If only someone would pan the camera over. Oh, okay. There we go. So let's see here. 3, 3, 3, 3, 3. Lots of 3s, all right? And suppose I've got a 1 here and a 1 here. But that's it. Everything else is zeros. So here, the characteristic polynomial would be 3 minus t to the 1, 2, 3, 4, 5 But the minimal polynomial would be what, if you believe the thing I haven't proved, this claim over here?
3 minus t cubed.
Yes. Because that's the largest Jordan block. Yeah.
Does that mean that the minimal polynomial is just the characteristic polynomial of the Jordan form of a matrix?
It means what I said over here.
But is that equivalent to what I said?
I don't think so.
Okay.
I mean, I don't know what you said. Maybe. I'm not committing to it.
It's not, Michael. I thought it was. I think I may have told you that, but it's not. I figured that out last night.
So,
I mean, I'm going to do some problems.
uh-oh. So 2, 1, don't feel bad. I have labored under various misformulations of this in previous semesters of my life. Only this book, for me, I don't know, something about this, the presentation in Damiano and Little, it just gelled for me, and I can just see it now. I mean, it's obvious what's going on. I don't have to think much more about it. I mean, I think I'm pretty sure I understand it now. At least, I understand the result. And I understood the proof when I read it. But understanding the proof when I read it and being able to prove it to you here, different things. And anyway, we don't need to do that today. So here, again, your characteristic polynomial, you can read, that's just, it's always, the characteristic polynomial has the order of the matrix, right? If it's a, what, 2, 4, 5, 6, this is 7 by 7 matrix. It has a 7th order characteristic polynomial, right? So, and the characteristic polynomial is easy. It's just, 2 minus, silence, woman. 2 minus,
Whoa.
what? I own her. I'm allowed to do that. So does that make it worse?
That's misogyny.
I don't own her. She's just paid for by commercials on my phone. If I paid $1, I would own her. So,
I'm such a slave.
well, you'd have to ask somebody else about that. I won't say who. Let's see, 3 minus t. You do 3 minus t cubed would be that good characteristic polynomial. The minimal polynomial here will be what? See, so this time, the biggest block, there's 2 biggest blocks to the same size. And so, it's just what? 2 minus t squared times, and you also have to have 1, but you don't have to have more. And basically the point here is, because there's this direct sum decomposition, when you look at a minus 2I squared, that puts all of these to 0, right? So when you square it, that just, these things go to 0, and this stuff stays intact, right? But on the other hand, when you look at 3 minus I, or sorry, a minus 3I, this leaves this stuff non-zero, right? But it makes this lower block 0. So when you take the product of these 2 things, they both have trivial upper and lower blocks, and when you multiply them, it just gives you 0. You can start to see why it is the length of the longest chain is what you need, because using the length of the longest chain for the minimal polynomial forces that block to square to 0 when you start powering it. That's a sketch of the proof, but not the real proof. Anyway, so that's kind of it.
In that example, also J was the size of a Jordan block faux linear, or is it 4?
Oh, faux Landry
Do we
J.
get
Yeah, sometimes my mind skips. Okay, so there's 2 obvious theorems you can say, right? The one theorem you can say is if each distinct eigenvalue, right, appears in the minimal polynomial with order 1. So if you have like t minus lambda I for each eigenvalue lambda I, and that's all you have, that means that your linear transformation is diagonalizable. Because what that means is that the largest Jordan block you have is a 1-by-1 block for the each and every eigenvalue, which is to say that you have enough eigenvalues to form an eigenbasis, eigenvectors to form an eigenbasis. On the flip side, you can ask the question, what does it mean when the minimal polynomial is equal to the characteristic polynomial? Right? That means that there's just 1 Jordan block for each eigenvalue. So the characteristic polynomial is equal to the minimal polynomial if you have something like this. 1, 0, I, 1, I, count up. 3, 3, 3, 1, 1. I don't, it doesn't have the ones, could you just tap? Sorry, not using mine. Not being consistent. My blocks should be these. I don't know, I'm not a slave to this notation. The point here is the minimal polynomial would be equal to the characteristic polynomial because each eigenvalue, 3i1, is just one Jordan block. But 3 has 3. Thank you. I just killed my own example. Good job. Okay. Now, you'd have P of T is equal to G of T. Well, would you? G of T has to be monic. Is this monic? 3, 4. Aha! Yes, this will be monic. Because we have an even matrix, so -1 to the dimension of B is 1. So, okay. For odd, you got to worry about plus or minus, which, by the way, is the main reason other people in other books, instead of looking at determinant of T minus Ti for the characteristic polynomial, they look at Ti minus T. That forces the characteristic polynomial to be mnemonic. But it introduces a host of signs other places you don't want them, so that's why we don't do it. Because as much as we love the theory of polynomials, we don't love it that much. It's a very small part of this course, right? In fact, I'm just showing you the window into the next level of linear algebra. Advanced linear algebra is all about the study of polynomials in modules. Anyway, so you guys have a question about your homework? Yes, Landon?
So if you took away, like, okay, so say you have like the 2 minus t to the 4th, 3 minus t to the cube, and if you took like one of those things away that correspond to the cycle, one of the powers that correspond to the cycle, then would it not be 0?
You mean if I made it a square,
Yeah,
then it wouldn't annihilate T.
yes. So, then like, so.
There would be a vector such that 3 minus big T squared acting on X is not 0.
And that's why, you're only trying to get to 0, so that's why you don't have to throw all the other stuff in there. That's what makes it a minimal polynomial.
Right, I mean, by our definition of IT at the start, looking at,
Okay.
set of all polynomials which annihilate T. Yes, in the sense of sending it to the 0 operator, yeah.
Does that conclude our study of linear algebra?
Yes, pretty much. I would point out, there's something I said the other day which is really important for your homework, right? Which is to test similarity of two matrices. What do? Do they have the same Jordan form, right?
So you find the Jordan form and then figure it out if they're the same.
Right. Or if you're lucky, you can show they have different determinants or different traits. A kind professor on a final exam might allow you to show that they're dissimilar by showing they have distinct traits or other things. In fact, to show, but the proof that the Jordan form of two being the same makes them similar basically boils down to showing that eigenspaces are preserved under similarity transformation. Not the eigenspace itself, but the dimensions of the eigenspaces. And not just the eigenspace, but the generalized eigenspaces of each order.
So the number of bases doesn't change. The number of elements of the bases doesn't change.
Right, like the relative dimension of the kernels of T minus lambda I restricted to the eigenspaces, that is an invariant under like the similarity transformation. And of course, the dimension of those kernels is what defines the Jordan form to be what it is. So consequently, checking Jordan forms being the same gives you similarity. There's other fun things you can do. Like here's a simple question. If I give you the Jordan form of A, what's the Jordan form of A squared?
The Jordan form of A.
If I tell you A has Jordan form J sub A, then I say, what's the Jordan form of A squared? What would you do?
Is it the Jordan form squared?
Yes.
I thought so.
How do you prove that?
Oh.
Use the definition by the similarity transform.
Right, this is an old question in a new light, right? So JA is equal to P inverse AP because it's a similarity transformation of A, right? Where P is formed from the Jordan basis, like, which we almost proved the existence of. And so if I take JA squared, what do I get? I get P inverse AP, P inverse AP, right? Which is P inverse A squared P, which shows you that the Jordan form of A squared is similar to A squared, right? And that suffices to prove that the Jordan form of A squared is just the Jordan form of A parentheses squared. Stupid English. Sorry. Sounds like I'm saying thing is the thing, but I'm actually saying something. Questions about your homework? Yes? No?
So for the spectral decomposition,
Uh-huh.
when you're finding
problem with
the
that one?
projections on your eigenspaces, do you have to use an orthonormal basis to find those projections? Or does it just have to be an orthogonal basis?
Well, if you use an if you don't use an orthonormal basis, then the Gram-Schmidt algorithm has to be modified to reflect the fact that you're not projecting with vector space by a unit length. The modified Gram-Schmidt algorithm that is for an orthogonal basis. So if you suppose you're given a set of vectors v1, bk, you want to run Gram-Schmidt algorithm unnormalized. I'll just say no norm. No normalization. So your first thing is u1 equals to v1 because you don't care, linearly independent of course, because you don't care if it's normalized or not. That's just the first thing. And then your second would be, well, it'd be v2, right? But then you got to subtract off, well, what you got to subtract off really is v2 dot v1 hat times v1 hat. But what was v1 hat? v1 hat is the unit vector in the direction of v1. So what that is that's 1 over the v1. V1. I think I'm missing a square root. I mean, I don't think I know I'm missing a square root. There it is. So that's normalized. That has length 1. That's the unit vector in the direction of v1. If you like, you could write v1 divided by length of v1. Right? In fact, I can't help myself but to say this. v1 is equal to the length of v1 times v1 hat. This is a wonderful formula. This says that any vector can be written as a magnitude times a direction. It's also true in the inner product space. Anyway.
Oh, okay. I was asking
So that's
about the spectral decomposition.
yes, but you're asking me about can you do things with projections based with non-orthonormal sets?
Oh, okay. Yeah.
So
the answer is no.
I mean, well, yeah, but the in short, if I have v is equal to c1 v1 plus da 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 plus cn vn, I should use u's. And the u1 un are just orthogonal, but not necessarily orthonormal. Then when I go through the calculation to figure out what these coefficients are, for example, I've got like v1 dot uj, right, is equal to cj uj dot uj. But the thing is, that's not 1 anymore. So the coefficients c sub j are what? They're v dot u sub j divided by the length of u sub j squared. And so every place that I previously had this in my orthonormal formulas, I have to replace with this over that in the orthogonal formulas. So yeah, you can build projections, like for example, the projection, if this was an n, if this was k. So suppose u1 through uk spans a subspace, right? Right. Then the projection onto that subspace would be equal to the sum. Say j equals 1 to k of v dot u sub j divided by the length of u sub j squared times u sub j, right? Before, the formula we had for projection was just the top thing, because this was 1.
Okay, that makes sense.
So yeah, you can modify it, but I didn't until now. So is that the best way? I don't know. Maybe I just, there's a question. Do you want to normalize? Do you want to have ugly formulas? Somewhere or another, you're dividing by this stupid thing. Whether you admit to it or not, it's there. Are you going to divide by the construction of the basis, or are you going to divide in the formula? I mean, it's somewhere you have to face the music of the square root of blah, 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 blah squared. I think that's the ugliness calculation way. It's there somewhere. Unless you're one of these people who wants to work with the matrix. There's a way of doing this all with matrices and the transposes that I don't teach. But that's pretty close to that spectral decomposition formulas that you've seen. Those are actually matrices, but I don't so much teach that as a calculation method as I teach that as just something that's an aspect of the spectral theorem. Other people use those projection matrices we found in the spectral theorem as the thing to build the projections from, right? If you did that, then you get away from using the basis directly. But anyway, there must be another question before I blather on what this is.
For number 153, it says find the line closest, and then it gives us 4 points.
Yeah.
I was wondering how to do that.
What?
I was wondering how to get started to do that.
So this is just a standard linear least squares problem. So I showed you guys that if you have an inconsistent system of equations, you can find a solution to the normal equations to find the best approximation to the solution. So in short, what you do is you feed the data into y equals mx plus b. All right. So just for the sake of example, suppose I had data points 1, 2, 3, 4, 5, 6, 7, 8. Hopefully those aren't on the same line. That would be my line. And so what does that mean? That means that 2 is equal to m plus b. That means that 4 is equal to 3m plus b. That means that 6 is equal to 5m plus b. That means that 8 is equal to 7m plus b. See, I'm just plugging the data into the model. And then so as a matrix equation, that becomes 1, 3, 5, 7, 1, 1, 1, 1 times the mb vector is equal to 2, 4, 6, 8. So give this a name, call this thing big A, call this thing big B. Define, that's an inconsistent system of equations, right? You have 4 equations, 2 unknowns, and those equations are inconsistent. You can't solve it directly, but the best thing you can do is solve the so-called corresponding normal equations. What you do instead is you solve A transpose A times, MB is equal to A transpose times AB. These are the so-called normal equations. The solutions to those give you the best fit line to the data set. That is how you do it. There is an explicit example in my notes. I did not work through it in class, but you can find it in there. Does anybody remember?
I think it's like 9.5.
9.5.7? Sounds about right. 9.5.7, somewhere in there. It's in the geometry chapter. It's I don't remember. I can find it for you.
It's 9.5.9 actually.
9.5. Sorry.
It's like, oh, you're right.
Landon,
What?
you better get it right now.
I did write it down.
How dare you, Landon? I'm just going to call you Professor Landon from now on.
Oh, I lost my.
Strip you of your doctorate. We're Dr. Professor Landon. It's okay, he'll win me back.
So when you write O, you don't lose.
Just try to be with Damiano.
Damiano. I don't know. I'm mispronouncing it every time a different way. Anyway, other questions?
Patrick, you must teach me to draw.
Draw.
Number 157. I don't have a book. Can somebody?
Yeah.
What is the book?
It's very simple.
Oh, okay.
You have your regular axes, then you need to draw your eigenaxes, whatever they are. I want to actually look at the license, right?
That's it.
So you draw the eigenaxes, and then you look at what does the equation of the thing look like in eigencoordinates, right? So like, just as a hypothetical, suppose you had q of xy equal to blah, actually x1, x2. All right? And then you look at the characteristic equation, you find eigenvalue lambda 1 equals 2, you find eigenvalue lambda 3, lambda 2 equals to 1, all right? And you find that the eigenvectors corresponding to those eigenvalues are like V1, which is, say, 1 minus 1, and V2 is like 1, 1. So that would be the picture I have here, which may be like your homework problem. The eigenvectors, not the eigenvalues. Okay. So if the eigenvalues were this, 2 and 1, and my eigendirections, 1 minus 1 and 1, 1, there's a plus or minus to choose here. You gotta be careful. That well, anyway, so like that. Then what this means then is in the eigencoordinates, the equation is just 2y1 squared plus y2 squared, right? Now, if your original equation was blah equals to 1, then your eigenequation, the 1 transforms to 1, so it's still 1. And then, so that's the equation you're looking at in eigencoordinates, the rotated coordinates. They have to just be rotated coordinates because we proved that a symmetric transformation has an orthonormal eigenbasis, which means that these V1 and V2 can be chosen to be orthonormal. Oops. Thanks. Orthonormal. And so, the new axes will be perpendicular still, and just a rotated version of my original axis by the spectral theorem. And so that's, if this were the eigenvalues, that would be the equation, and what is it? Well, it's an ellipse, right? It goes, when y1 is equal to 0, y2 is plus or minus 1, right? So, it'd be like here and here, moving up the scale. And then, let's see here, when y2 is equal to 0, which would be on the y1 axis, right? What do you got? You got, y1 is plus or minus what? Yeah, square root 1/2, so it's, I don't know, something like that. So what you got is an ellipse. But it's a tilted ellipse, right? And it's a tilted ellipse with the symmetry axis of the tilted ellipse corresponding to the eigendirection. And that's the significance of eigenvectors as they apply to quadratic forms. The eigenvectors point in the symmetry axis for the conic sections, which have been rotated in the original formalism. Right? If you write an equation like this, if you go back to pre-calculus and try to, or college algebra or whatever, and try to find where did I study rotated ellipses and rotated hyperbolas and stuff, if you took that course in this country, you probably haven't, because those are complicated. They involve cross terms like x, y. The formula has something like x1, x2 in it, and we don't really study stuff like that. x1 squared plus blah plus x2 squared, stuff like that. We don't know how to graph that before we have linear algebra. So I'm showing you now that the way you graph that is to understand what are the eigenvalues for the quadratic form, and you discover the eigendirections. That shows you what the true nature of the quadratic, what the true conic section is in terms of the eigenaxes.
So if you have two for like that.
Answer. So I'm not looking for like a super awesome picture. I'm mostly hoping that you understand the relation of the eigendirections with respect to that, and the significance of the eigenvalues as they relate to it being a hyperbola or an ellipse or parabola. Yes.
So basically, if in one eigendirection you have a 0 for the eigenvalue, it's going to be a line, right? Or something.
Right, a pair of lines. If we're looking at if one of the eigenvalues is 0, then we'd end up with something like lambda 2y2 squared equal to 1 or something like that, which would end up giving me y2 is equal to plus or minus 1 over the square root of lambda 2, I guess. Yeah. One of them's negative, one of them's 0. So you'd have no solutions. Oh, of course. Well, anyway. That's not surprising. This quadratic form, you can graph that. What's the graph of this? Never mind.
What?
Give me a
What's the graph
complex
of this?
number.
There's, I don't know what you're talking about. Real. Keep it real. There's none, right? There's a. So not every quadratic form has a graph. course, if I just change this to -1, then you're like, oh, well, they're vertical lines, plus or minus 1. Right?
What if you get like a fake one, like the imaginary one, and then you get like one real one?
That's fighting words. That's imaginary. Anyway, I don't know, I don't know how to think about it, but do you guys have any other questions? That you're stuck on? All right, well.
Wait, time out.
When specifically is it due? Like,
5.
Okay.
In your office or the back?
In my office, or you better not, if you wait till 5, the engineering locks down sometime close to 5. I'm not sure exactly when access and control locks those doors outside my office. Not my office, but the hallway door, so beware of that. So that when I say 5, I mean whenever the doors close, I can't help you get in if it's 5. If it's 4:59 and that door is clocked, if the door is closed, it's not within my power to fix that,
What time are you leaving?
Probably a little bit before, actually, I'm coming back at 5 to get the whole thing. So,
Wait, so can we put it in your box, you said, or not?
yeah, you put my box, or my box or the office, whichever.
Okay.
Where's your car park?
Hopefully going to go to campus to get my keys. Maybe. I recently learned my office is not going to be constructed, so it's very exciting. That's an office involves. And it's not constructed from some sort of,
They're destroying the terrible classroom.
they're just moving it. And they're killing your break room.
Sorry, does the math department have a break room with a foosball table in it?
We have-
Vending
we will
machines?
have-
We want to learn.
We will have just as many break rooms as the engineering department next semester.
I mean, we still have an atrium, so.
Anyway, I think that's all we have for today.
I have a question.
I
guess there's no disadvantage.
Oh,
Okay, so yeah,
the quiz is written. I will post it.
And we'll just do it Monday, we'll go over it on
It will be due on Monday. We'll go over it on Monday. That is true.
We all still need to talk to someone about that.
I will also.
We need to make a figurine.
I just say your parents said that. He says they're going to use the evidence. I said, so I can't get today. I'm just working fast. I see the mind.
Get it done. On Monday, so it's our last class. But I can think of.
No, his wife died.
Oh, I'm just saying.